Today our guest is the astrophysicist Katie Mack. Now, when she's not pondering and coding the secrets of space, Dr. Mack's well known to many as a popular scientific tweeter at AstroKatie. And she's also the author of a new book about the fate of the universe. We'll get to all that later. And this being Numberphile, you can also rest assured I'm pretty curious about the role of mathematics in the life of a cosmologist. Can I first ask, Katie or Catherine?
Katie.
Because you're Katie on your book, but you're Catherine on your papers.
Yeah. It's been a sort of change over time. It's just because I have the AstroKatie thing, people don't know who Catherine Mack is, in the general public. And with my papers, when I started writing physics papers, I would use my full name as seemed appropriate. And so I've diverged into these two different people now.
There's no possibility of switching to Katie on your papers then, because then it will cause this kind of disjoin, or
because then I would have two different names on my you wouldn't be able to find all my papers all at once. So I have to be Catherine on the papers, and I have to be Katie in public stuff. It's just it's set now. It's like those authors who have different pen names for different genres. That's what I'm at.
All right, then we'll go with Katie for now. Then.
Okay.
Where are you from? Where were you born?
I was born in Long Beach, California. Just sort of LA area, and I've been my career has taken me sort of roughly east continuously. So I did undergrad at Caltech and then grad school at Princeton, and then I continued east to Cambridge for my first postdoc, and then wrapped around to Melbourne for my second, and then wrapped all the way around back to North Carolina for my faculty job.
You're just doing laps of the Earth.
Yeah, basically. Yeah, I don't know where that suggests I go next, but I guess we'll see.
If I had been following your childhood, at what point would I have said, do you know what? I think that girl's going to become an astrophysicist.
I mean, if you had asked me, I would have told you that around 10. So specifically, I wanted to be a cosmologist at that time, because that was around when I first started reading stuff by Stephen Hawking and, Paul Davies and like all these, all this stuff about the Big Bang and time travel and space-time and black holes. And that was all fascinating to me. And when I found out that the job Stephen Hawking had was called Cosmologist, I was like, okay, that's what I want to be. That's my goal now.
Were you a pretty nerdy girl then?
Yeah.
Did you have geeky interests, or were you?
Yeah. I mean, I was super nerdy and super sporty. So I was kind of in both those categories. I did track and field and basketball, sort of the whole time growing up. I was always running around doing some kind of sport, and then I was also doing things like going to a planetary science summer camp. So I was I was definitely very much in both of those categories as a kid. And I was like winning championships in high jump, stuff like that. So I was I was a pretty serious athlete at the time. But in the end, the physics did win out. Like when I was choosing high schools, I was being recruited by the local high school track team at the same time as I was eyeing this little math and science magnet school where I could totally nerd out. And I ended up going in that direction and sort of heading toward that side of things in my life.
Was high jump like your speciality?
That was the thing that I was sort of best at. But I did all the field events, shot put and javelin and triple jump and, long jump, all of that stuff I really enjoyed.
What's your personal best high jump?
It's a little bit over 5 feet.
Okay.
Yeah.
So in feet then, not we're not going metric.
No, not in California we weren't. No.
So athletics and sport was like a proper option, was it? Like
I don't know. I wonder about that. I wonder if I had gone to a more sports oriented high school, if I would have ended up getting super serious about sports. But I think I was always enough interested in science and that kind of career that I probably wouldn't have gone too far. Although, when I was at Cambridge, I knew a graduate student who was, while she was doing graduate school in astrophysics, was also on the Olympic diving team. So,
Right.
people do that. But I don't know how far I would have gone with it. But I did love it, and I was pretty good. I think it was when I was in middle school, I won the all-city championship for high jump, which is why I was recruited by the high school. But
When did you last do a proper high jump over a bar onto a bag?
it was a while ago. I think I did a little bit of practice while I was a postdoc at Melbourne. Like I sort of snuck out into onto the practice field. But it's hard once you're not a student. If you do running or basketball or something like that, it's very easy to just continue that through your life. But if you do something that involves, heavy duty equipment, it's very hard to just casually, casually high jump. Like it's not really an option, which is unfortunate because I did enjoy it a lot.
So you'd probably snap your spine if you went out and did one now.
Well, I mean, there's that, but also like I don't have, I don't have like a huge pad and these giant metal stands and a big pole to put across them. Like I just don't have that stuff lying around, and there's only so much you can do onto like your mattress before you injure yourself. So
I was going to say you don't do the occasional Fosbury flop into the bed or anything.
No, I don't think that would be a good idea.
All right then. So through high school and whatnot, then school, you were like pretty academically sound. Then were you like were you the top of the class, physics, mathsy person?
I was up there, I was I did pretty well on that stuff.
What was your attitude to mathematics at this point? I have to ask because it's the Numberphile podcast. Obviously, you've got these physics aspirations, but mathematics is so intertwined with physics, obviously.
Yeah, of course. Yeah, I've always loved math. When I was in middle school, I think I was in the math club, and I would do those sort of math problems for fun, that kind of thing. I never did the competitions, but I enjoyed the practice of it. It was a little bit harder in high school because the high school I was at had this sort of experimental math program that was built around real world word problem kind of things and group work and collaboration, and I think that can be very useful, but it didn't get into the kind of math that I really loved, which was, sort of the sort of more technical, more abstract stuff around, proofs and all of those kinds of things. We didn't really get into that. And so my math skills really, really sort of faded in high school, which was a bummer because I really did love math, but it was just the kind of program that wasn't suited to what I wanted to do and the way I like to learn. So that made it a little bit difficult. And when I ended up at Caltech as an undergrad, I really had a lot of catching up to do on the math side of things.
I get the impression from that little bit I've read about you that you had quite a good family for where you wanted to go. Like you would have probably had parents who were quite encouraging. Well,
my mom is super academic. My mom has far too many college degrees. So she's retired now, but she got her PhD in nursing and spent a long time working in sort of various aspects of medical things, and then became a professor, and also at some point got a law degree, and has been teaching things like health law and aspects of that as well. So she's very much in the academic side of things. So she's been sort of in school for most of my life growing up in one way or another.
Right.
And she's always been very very encouraging about my sort of physics and science interests in general. And she would like take me to the observatory when I was a kid, and we'd drive out to the desert to watch meteor showers, and she would take me to, if Stephen Hawking was giving a talk at Caltech, she would drive me out to watch that, and those kinds of things. She was always very very encouraging of that.
And what did your dad do?
He was sort of in a number of different odd jobs, not really. He just did a number of different things, but wasn't really into academics at all. So very different.
I read that your mother encouraged you to watch Star Trek and Star Wars. Is that true?
She was into science fiction. She's always been into science fiction. So she was into Star Trek a lot. When Star Trek, when the original series was canceled, there was a big sort of popular protest about it. People were like picketing the studio trying to get it reinstated, right? She was part of that.
Yeah.
So she was she was very into Star Trek. And
I can see how proud you are.
Yeah, of course. When I was growing up, she had subscriptions to these science fiction magazines, and I used to take the magazines when she was done with them and read all these science fiction stories. So she and I share a love of science fiction for sure. Do
you have a particular preference here in the Star Wars, Star Trek thing, or is that like too hot a subject to even venture into?
They're both fine franchises. I like Star Trek a lot. I like the sort of utopian vision of Star Trek a lot. So that's my sort of the direction I lean in that debate, I think.
Okay then. As an undergrad, you said you went to Caltech, did you?
Yeah. I did physics, just the ordinary physics major. They have an astronomy major there, and it's very similar to the physics majors. There's a lot of overlap. But I wanted to do physics because I thought that it would be maybe a little bit more flexible in case I wanted to go into like particle theory or something like that.
Can you tell me a bit more about the mathematics thing then? It sounds like you said you kind of felt like you were a bit behind the curve to start with because of the alternative education.
Yeah.
Was that dangerous? Did you feel like you were sort of sinking at any point, or was it something you always had well in hand?
It was a challenge. When I first arrived at Caltech, there are these sort of placement tests you take when you first get there for placement in physics and math. For the mathematics side of things, when you start, the first year mathematics is called Math 1, right? Like it's the first step, and there's a special section of Math 1 that they reserve for people who are a little bit behind and need catching up, and they call it Math 0.9. So that's where I was. I was in Math 0.9 when I first got there. It was so there was a lot of catching up to do, and when I was taking my physics courses, it was a big challenge was that we'd have these timed exams, and it would just take me a lot longer because I didn't have the sort of mathematical rules just like right at hand in my mind. And so I would have to sort of rederive everything during the test. and that made it a lot harder to complete the exams in time. It was harder to keep up with classes. So, if I had to do it all over again, I would have done a lot more preparation in mathematics before getting to Caltech. But I mean, I got through. Like it didn't stop me, but it did make things a lot harder.
You said that you did physics because you wanted to keep your options open.
Yeah.
Were you ever tempted or nearly seduced away from that cosmology astrophysicist path? Like, were there other things you saw that you thought this might be for me, or did you pretty much stay on the straight and narrow throughout?
Well, I started in experimental particle physics in terms of the research that I did. So I did dabble in other areas of physics.
Yeah.
I was never tempted away from physics as a broad field, but
yeah.
I started doing stuff in particle physics when I was still in high school, actually. So I had this very weird and cool opportunity to go work at the Super Kamiokande neutrino detector in Japan while I was in high school. I mean, I went there and spent some time like running shifts at the detector, not doing anything important, but taking radon measurements and making sure the data collection was working and everything.
Yeah.
So
Is that the one that looks really cool inside?
Yeah.
Like it looks like a art installation. Did you get to go in it many times?
I did. I did get to go in it. So the first time I went, I was just running shifts at the detector, so I was just sort of sitting in the control room. But then when I was in college, I went again while they were upgrading the machine. And in that instance, in order to do the upgrade, we had to go in and replace these giant photomultiplier tubes, these things that look like huge light bulbs, basically. We had to go through and replace the wiring on those. And so I got to sit in this little boat and go around and replace these things and do a bunch of like electronics on the.
I'm so jealous. I so want to go in that boat. I've seen pictures and I'm like, it's my dream.
It was very cool. So most of the work we were doing was on the outer detector, which is sort of this cylindrical region between the big inside part and the outer wall. So mostly we couldn't see the huge, cool inner detector that you always see in the pictures. But I did get to go inside the inner detector at some point. So I have been
Very
inside
cool.
it. It is very cool.
Very cool. All right. So you started with the particle physics.
Yeah.
What happened next? What was the path? Give me the executive summary.
Well, so I started, so I worked on Super Kamiokande. I worked on this long baseline neutrino experiment, K2K, where from another part of Japan, you shoot neutrinos at the neutrino detector and then observe what happens to them. I was pretty involved in that project, and I enjoyed it. It was interesting, but it's just this huge, huge collaboration. And the part that I did just felt like a very, very small piece. And so I wanted to do cosmology because, you could be a little bit more flexible, a little bit more sort of creative, try and answer these big questions in weird, interesting ways. And you wouldn't have to be stuck on sort of one experiment measuring one number for years and years. And so to me, cosmology seemed like a freeing kind of thing. And it was funny because when I first got started in research, I was doing this experimental stuff, and I had this sort of impression that to be a theorist, you had to be like, a super genius. And I thought like I couldn't possibly go into theoretical work because I'm not a super genius. And it took a while of being in physics before realizing that actually, like everybody there is smart in one way or another, but it's not like the theorists are the really smart ones and the experimental ones are less. That's just not how it works. Everybody is doing interesting things in different ways, and it's more about what kind of work you like to do, the ways you like to think and the ways you like to approach problems. And I started getting into theoretical astrophysics work at the end of undergrad, and I just really enjoyed it. And it wasn't sort of inaccessible in this way that I had thought of it as being. And so then when I was in grad school, I just totally leaned into, cosmology as the thing that I really wanted to do.
Help me understand being a theoretical cosmologist or theoretical astrophysicist, because what does your work look like? Take away the teaching, take away outreach and all the kind of add-on things, and just the pure sort of research doing science part.
Yeah.
What does that work actually look like? Because to me, the few people I know who do this, it seems to me like you just get to sit down and dream up some idea and then do a few sums and think, oh, yeah, that could work. And then what? Like...
Yeah, so it's, like I spend most of my time in front of a computer. I think that's true for people in all areas of physics and astronomy these days. And I do a lot of coding, and that's also true for most people in my field in any subfield of astrophysics.
But coding what? Coding programs that will run your ideas, or? Yeah,
so the way it usually works is First of all, the ideas generally come from having conversations with people. So, you go to conferences, you do collaboration visits, you bounce ideas off of people, you sort of come up with stuff, and you come up with like, maybe there's a way to measure this particular thing using this particular observation, right? So you try and connect some idea from the theory side. So some new proposal about, maybe something about how dark matter works. You try and connect that to an observation that can be made with an actual telescope or an experimental result or something like that. And then you go through and you start on the theory side and you try and figure out, like, in a certain environment, in a certain situation, what does the theory predict will happen physically? So that's the phenomenology side of things, trying to work out what the theory really predicts. And so that involves reading a bunch of papers, writing a bunch of equations, sort of working out the order of magnitude of what's going on in that sort of system. And then you look at what the literature is saying about the experiments that are going to happen, or the observations that are going to happen, and see what the sensitivities are, see what they can actually observe, and you try and make a connection between what the observations can do and what the theory is predicting. And so in this is sort of in my area of theoretical cosmology, which is often called phenomenology, where you're really sort of in that middle space between the theory and the observation. And so what you put in the computer is, the coding is where you put in, here's all the parameters of the theory, here's the relevant equations. If I tweak this parameter, this is how this will all flow through. This is what the prediction will be for the physical property that can actually be measured. And then sometimes you have to do some kind of random thing where you choose a bunch of possible parameters and try and work out constraints or limits or whatever. So you do a lot of that sort of thing in the code. But yeah, it's mostly the code is for solving a lot of equations quickly to carry through whatever you've worked out on paper.
What happens if you are lying in bed one night and you come up with a theory of how the universe is working, and it's something that can't yet be or hasn't been measured and can't be measured or observed?
Yeah.
Do you then have to put that on a shelf, like as a scientist, and say, well, if I can't get any measurements to go with it, it's pointless to even think about it? Or what do you do when that happens? What do you do when your idea is something that can't be looked at with a telescope yet?
People do write papers about that. I don't usually, because I'm not on the model building side, so I tend not to come up with new theories of how things work. But I mean, you can always write a paper about, here's a cool new idea. Here's how it could be measured in 50 years with a certain, extremely powerful telescope. So,
and then hope you stay alive long enough to get a Nobel Prize.
Hope that somebody will put together a better telescope sooner. That's also a possibility.
Yeah.
But yeah, a lot of the work I did, early on in my career was about high redshift 21 centimeter astronomy, which is where we're trying to use low frequency radio telescopes to measure the neutral hydrogen in the epoch of the first galaxies, basically. And a lot of that work is going to be done by an instrument called the Square Kilometer Array, which is still sort of a decade away from really producing the kind of data that'll be useful. And I've been writing papers about that for years, about what that will tell us. So it's totally permissible to write papers about what future instruments will do, and that's often necessary to get those future instruments built. So it's okay to theorize something that can't be observed at the moment, as long as you can express how it will be observed in the future.
It sounds like you've got to have some decent coding.
Yeah.
How good mathematics do you have to have when you're doing sort of physics at your level? Is it like super Jedi mathematics that's really good, or would mathematicians think what you're doing is pretty basic stuff, really? I have no sense of how good you have to be at mathematics.
So it depends on what area you're working in. The kind of stuff that I'm doing right now, generally I deal a lot with differential equations, but other than that, I don't, I'm not doing, if I were working in general relativity theory, then I would be doing differential geometry, which is complicated, right? That's quite sophisticated mathematics. If I were doing string theory, then I would be getting into a whole lot of really advanced sort of calculus kind of stuff and differential forms and a whole lot of more complicated, more sophisticated mathematical stuff. And if I were doing data analysis, I would have to do a whole lot of statistics, and I'd have to have a very deep understanding of statistics. So it really just kind of depends on what area you're working in. If you do quantum field theory, you're working with path integrals all the time and, doing a lot of sophisticated stuff around that.
Yeah.
It's very dependent on the subfield you're in. In a lot of astrophysics, you don't do a huge amount of really complex mathematics unless you're doing sort of model building. You're doing the kind of theory where you're coming up with, new models of particle physics or whatever. And then it tends to get more abstract. But a lot of us just kind of do a lot of differential equations all day, and we use the computer to do them. So it's not day to day. It's not always that mathematically complex, but it certainly helps to be very conversant in a lot of these ideas just so that you can understand what's being written about in the papers. You can kind of visualize the computations. You can understand, even the things that are being plotted are sometimes plotted in a particular way in order to bring out some aspect of the physics. And so it's really helpful to just have a good facility with all of that stuff.
So you're getting away with your math 0.9 at the moment, are you?
At the moment, yes, but occasionally I have to push myself all the way up to 1. Hold on a sec. I just need to pour myself some more tea. Okay.
We'll take this quick tea break to remind you that this episode has been sponsored by G Research, a world-leading quantitative finance research firm based in Europe. And if you find quantitative easy to say, well, you're a better podcaster than me. Now, G Research is hiring clever people from around the world to tackle the biggest questions in finance, applying the latest in machine learning, big data, all the top technology. G Research is always looking to hire the top STEM talent, so if you are good with numbers, mathematics, computers, that kind of stuff, well, maybe this could be the opportunity you've been waiting for. I know G Research takes real pride in the culture they've created, and they're keen to nurture future talent. To find out more about them, go to gresearch.co.uk/Numberphile. G Research. Create today, predict tomorrow. Can I ask you about Twitter?
Sure.
One of the things you're quite well known for, it's for how I first knew of you, is for being Twitter famous. You were kind of the first scientist to become really mega followed on Twitter, and you're the person to follow, and you're still one of the most followed scientists out there. Tell me about why you joined Twitter first, the circumstances under why you were on Twitter in the first place, and then what happened.
I mean, I first got a Twitter account in grad school at some point, and I didn't really do anything with it. I just had the account. But when I was a postdoc at Cambridge, there was a colleague of mine came and gave a talk at some point about, I don't know, active galactic nuclei or whatever he was working on. And on his title slide on the talk, he put his Twitter handle. And I thought this was a very weird, I mean, this must have been, I don't know, 2010 or something like that. It was a while ago, and it wasn't, people were not doing that. Like, serious people would not include a Twitter handle on a title slide. Yeah. That was a very unusual thing. And so I thought this was really intriguing, and I looked at his Twitter account, and it was all astrophysics. It was very, I don't know, science-oriented account, and he would tweet about new results or interesting papers or the stuff that he was working on. He would live tweet conferences. This was a thing that people would do a lot at the time. And I thought, well, this is an interesting thing. Maybe I should try this out, and maybe this will be an interesting way to talk to more people about astrophysics. And so I thought, like, I should do this. And then a couple of weeks later, I was visiting Oxford University for a conference about dark matter, and my colleague was there, and he had planned to go to the conference, but he wasn't going to be able to attend the talks. He was based at Oxford, and so he said, "Hey, can you just live tweet this for me, so I know what I'm missing?" I'm like, "Sure, yeah, okay, I'll try that." Yeah. And so I just I did one tweet per talk, basically, to try and summarize what the talks are about. And Phil Marshall, my colleague, because he told me to do this, he would then retweet to his followers, and he had, I don't know, a few hundred or something like that at the time. And so that sort of got me into his network. And so I started to get followers, and I got really excited when I had a couple hundred followers based on sort of continuing that. And I found that it was just kind of a nice way to get to know other people in astrophysics, to get to know some people who were science writers interested in astrophysics. And then there were a few people who were just, interested in the subject, but not at all connected to the field. And I really enjoyed being able to talk about science in that way, to connect with people who were working on interesting things, but not at my institution, so I could kind of broaden my professional network. And then I just kind of carried it on.
Oh, so lovely and collegiate.
Yeah. Yeah, I mean, at first it really was, and I got to know a lot of people in a lot of different places, and then the Higgs, the Higgs boson announcement happened, and I was able to tweet about that, and that ended up like a couple of my tweets were picked up by blogs or newspapers or something about the importance of the Higgs, and so that kind of bumped me up some more. And I just found it was this really nice, really sort of broad community. I don't know, that worked really well for me.
Then what happened though? I thought you made a couple of clever comments and a couple of smart remarks and things kind of blew up.
Yeah, so
let's be honest here.
So a little while later, once my following had increased a little bit, and I was starting to become like a sort of known voice on Twitter. At that point you start to get comments, right? You start to get people trying to say things and get you riled up, right?
Yeah.
And so I would try to sort of address trolls and stuff in reasonable ways. And there was a very specifically impactful moment when I guess it was in 2014 or something, when there was so Brian Cox was on a TV show talking about something to do with climate change, and I tweeted about it, and I tweeted something about how climate change makes me really sad, because of what we're losing because of this process. And somebody, just some random person, tweeted back to say, that this was, this is all a scam, and climate change is a scam, and I should go learn some science. And so I replied something along the lines of like, I don't know, man, I already went and got a PhD in astrophysics. I feel like more than that would be overkill. And it was just, it was this reply that was just like, I think I was like walking down a hallway when I saw the tweet, and I just sort of, hammered out a reply, just something like to be like, yeah, whatever, go away. And I sort of chuckled to myself while I was typing it, but it was just a reply to him. I wasn't doing like the whole quote tweet thing or anything, I wasn't trying to make a scene.
Yeah.
But somehow some people saw it and started retweeting it.
Yeah.
And it just went super viral.
Yeah.
Suddenly like celebrities were screenshotting it. Like this whole exchange, and it doubled my following in a week. I went from like 40,000 to 80,000 followers or something like that. Somewhere in the middle of that, I got verified. I started getting messages from people like saying how much they like my Twitter presence. I got a call from like Huffington Post. I mean, it was just this really bizarre thing that happened, and that just really got me into this sort of very different category on Twitter.
Do you now feel a kind of pressure or expectation to occasionally be a bit sassy and clever now, and sort of and funny? Because I mean, that's such a great reply. Is the pressure now on to sort of be that person occasionally that swoops in with the witty remark? Because you do it a bit.
Yeah. So I think there's certainly pressure, I think, to be funny. I don't want to make fun of people. I don't want to be, mean. I certainly don't want to be mean to people who are, just kind of minding their own business or who are not like prominent voices, right? One of the things that viral moment showed me very clearly was how powerful and frightening that sort of attention can be, because I got a huge amount of attention, and it was almost entirely good attention, right? Like it wasn't like people were saying nice things for the most part, but it was still just totally out of my hands. This was like I was getting hundreds and hundreds of messages every day, and I was showing up, quoted in newspaper articles and stuff, and I had no control over that, and that's a scary thing to be suddenly thrust into this big spotlight. And at the same time, people were really ragging on this guy who I was replying to. Yeah. Tons and tons of messages about how stupid he was or whatever. And he was kind of a jerk, so I didn't feel that bad about him, but I still, I realized like how confronting that must be for him as well. And he was just some random dude, not a nice person, but not the devil, right? And certainly not a prominent person. I don't think, he only had a handful of followers. So I'm very aware of the power that having that kind of voice entails, and I'm very aware of how quickly things can go off the rails, and I don't want to put anybody in a position to be harassed, right? So I do try to be careful to not like attack people or not make anybody sort of the butt of a joke in a large context when they're just, just because I disagree with them. Because, if I sort of call someone out, there's, 300,000 people who choose to follow me, who would probably agree with me that person is wrong and might just be really, really abusive toward that person. And each person individually saying, "Oh, you're dumb," is not going to be that big a deal. But when you have a huge flood of it, it's a different story. And I've been sort of targeted by large online mob things in a limited way, and it's terrible, right? So you don't ever want to put someone else in that position. So I try not to use that avenue of expression too much. So, I will sometimes reply to people in a sarcastic way or whatever. And, I will sort of make my feelings known one way or another, but I try to be at least a little bit polite about it because I don't want to fuel that kind of attack mode.
Now, one thing you have tweeted about a lot is your book. Mm. I felt like I saw it coming. There was all this hype and expectation around it. Yeah. It's finally out. Yeah. It's gone down really well, hasn't it?
It has, yeah. It's been great. The response to the book has been better than I could have anticipated. I mean, I'm not really in touch with sales numbers per se, so I don't know. I don't have a good feel for whether it's done well on that side of things. But in terms of the reviews, every sort of professional review of it, in magazines and stuff has been positive, and the reviews on, Amazon and stuff like that are largely very good. So yeah. It's just been, that's been the thing that I really was worried about. When you're writing a book, you want it to sell well, I guess, but once you get the advance, it doesn't necessarily make that big of a difference to your life if it sells well or not, but you want it to be good, right?
Well, it makes a difference to whether you get to write another one.
It does get, yeah. Certainly, yeah. I mean, that's an issue, and that's in the back of my mind. But my first priority really with this book was just I want it to be good, right? Like I hope it sells well, sure, yeah. But I want it to be something that is, that I could be proud of, And yeah, the reception has been amazing, so I feel really good about that.
Now, it's called The End of Everything. Mm-hmm. Do I then say brackets astrophysically speaking, or do I just call it The End of Everything?
Either way, so technically the astrophysically speaking in parentheses is not a subtitle. It is part of the actual title, but I just call it The End of Everything mostly. Okay. The astrophysically speaking is in there because it was important for the publishers that there was something to indicate that this really, like, we really meant it. This is the end of everything. That it's not just like, metaphorically the end of everything. It's not like a novel about grief or something like that. It is actually about the end of everything.
So it's the end of everything, definitely with a capital E.
Yes, exactly.
And you look at basically how the universe is going to end, is that right?
Yeah, so different possibilities for how the universe might end, what they would look like, how we're trying to figure it out in physics and astronomy, what we're going to learn over the next few decades. But yeah, just the different possible ends of the cosmos.
This makes me think about a few things I always think about when I talk to people who do your job. Mm-hmm. And one is, what does it feel like to know that you're probably going to be dead when all this stuff happens? You're probably going to be dead when all the good stuff happens, all the stuff you think about and write about and research, yet alone the end of the universe. Mm-hmm. Just things like the end of galaxies and galaxy collisions and stuff. You're going to miss all that. Yeah. What does that make you feel?
I mean, it's a bummer, right? I want, I often wish I could just fast forward, a couple hundred years, a couple thousand years, million years, something. Just take a look, just see what it's gonna be like. And I'm really bummed that I don't get to see that. That there are astrophysical events that I can anticipate, but I can't ever watch. Like that's it's too bad. I mean, there's only so much one can do in one's lifetime, and you have to kind of accept that humans are mortal and we have these limitations on us, but we don't have to be happy about it. Like, I'm not happy about it.
So if I gave you the magic time machine bubble, and you could go anywhere forward, back, and also anywhere in space,
Yeah.
and just look at something for an hour, just to watch the sight, where would you take it?
I mean, I would have to think about that a lot more, but I mean, I would love to see the collision between the Milky Way and Andromeda. That's going to be, it's about 4 billion years from now, right? That's going to be really cool looking. And it'll take a long time. I would probably want to take my time machine there and then fast forward a while to actually see it carried through, but that would be really, really awesome.
But if you can only go to one place for an hour, I guess you just want to catch it like at its peak. Like, what's the night sky going to look like from Earth? Oh, there probably won't be an Earth, will there? But what's the night sky going to look like from around here at that point? It'd be crazy.
Yeah, I mean, there'll just be a lot more sort of light in the sky. That we'll have way more stars because all the stars from Andromeda will be a lot closer. When the collision occurs, it'll shove a bunch of hydrogen gas together and we'll make some more stars. You'll get more supernovae for a few centuries at least around that time. I mean, more like millennia, I guess. Around that time, you'll get more supernovae happening. For the highest mass stars, you get like sort of millions of years that these things burn. So you'll get the collision, you'll get some new stars forming, you'll get new stars blowing up. It won't be a huge amount of star formation because by that time a lot of the hydrogen will be depleted in both the Milky Way and Andromeda, but you'll get some fireworks. And then when the cores of the galaxies are coming together, the supermassive black holes will coalesce, and so you might get some really interesting sort of activity. I mean, even just at the beginning of the collision, you'll move gas around such that the black holes might become active. So you might get these giant jets coming out of the black holes, and they'll be tearing stars apart and stuff, and then they'll spiral together, and that could be really cool. I mean, it's going to be fascinating.
What about naming rights? What are we going to call the new galaxy?
People are calling it Milkdromeda. That's the
Milkdromeda.
Yeah, that's the term I've seen. I don't know. There maybe people will come up with something else, but
I mean, even the Andromeda Way is better than Milkdromeda.
Yeah. It's not up to me, but
not sure about that.
Yeah.
Do you know what? I love space and astronomy. Like, I really love it. But still, if I could have that time machine bubble, do you know where I think I'd go?
Where would you go?
I want to see the Titanic hit that iceberg.
It's so morbid.
I want to see that moment, what it sounded like and looked like as it hit. Yeah. Like, I'm not happy that the people died, and I don't want to, that's sad. I don't want to see all that. But I just want to see that collision.
You don't think that would just be terribly traumatizing and horrible?
I don't think the collision would be. Like, as it sank, it would be terrible and traumatizing, and what happened afterwards. But just that moment, because no one, well, I guess some people down below deck were hurt when that happened, but the actual collision, I think, was fairly innocuous.
You could just go watch an icebreaker plow around the Arctic Circle if you wanted to see, ships colliding with icebergs.
Yeah, but it hasn't got the historic significance.
True.
It hasn't got the historic significance.
And,
I would like to go and see a black hole up close as well, though.
Yeah. I mean, to see a black hole close enough that you could actually see the effects of the gravitational lensing would be very, very cool.
Yeah.
Yeah.
The end of the universe, it's such a fascinating topic. I'm not surprised everyone wants to read your book. But is it going to be a bit boring? Is it going to be a whimper? I mean, I guess I know you go through all the scenarios, but it's going to be a whimper, isn't it?
When I was thinking about the book, the structure of the book, one of the things that I considered doing was I thought, what if in the beginning of each chapter about each end of the universe, I put like a little science fiction-y vignette about, like what it looks like while it's happening and all this stuff. And I thought about doing that. And I realized like none of these are cinematic, none of these are going to be interesting to watch, because either you have a heat death, which is this very, very long, slow fading of the universe, or you have something that's so sudden that you don't see anything, like like vacuum decay, where it's just you don't even notice it happening, or you have something that is dramatic but only on this time scale of like millions of years, and that doesn't make a good story. Right. So some of them are more dramatic than others. I mean, a big crunch and a big rip are both very violent events and would be dramatic, but again, on the timescale of sort of millions of years rather than sort of human lifetimes.
So the Big Crunch doesn't have a dramatic final few seconds. It hasn't, like the Big Bang has a dramatic start.
Oh, it does.
Crunch.
It does get dramatic at the end. It's just by the time it's getting really dramatic. Well, okay, so the Big Crunch is an interesting case because you would see it coming, right? So if the universe were going to collapse on itself, you would see it coming because you would see that galaxies are moving toward you instead of away like they're supposed to. And you would see sort of the universe getting more compact. The part that gets dramatic is that the ambient radiation in the universe would start to heat up. Okay, so we have this background light in the universe right now called the cosmomicrowave background, which is the sort of background light from the Big Bang. This light that's left over from when the whole universe was hot and dense, when it was younger, when it was smaller. And that light is dissipated through the universe as the universe is expanded. But if the universe is compressing, then that light will be compressed, and so the universe will trend more toward that hot, dense state again. But it'll actually be worse than that because in addition to all this background light from when the universe was hot and dense at the beginning, the compressing universe would also compress all of the light from all the stars that have ever shone, all of the gamma ray bursts and all of the X-ray radiation and all of this other radiation that's been produced in the time since the beginning. All that light gets compressed as well, and it gets compressed and it gets shifted to higher frequencies, so it gets becomes harder radiation. There would be a time when you could sort of watch space heating up, and eventually it would get so hot that it would start to actually ignite the surfaces of stars.
Right.
So you get this situation where there's so much hard radiation in the universe that the surfaces of stars start undergoing thermonuclear reactions.
Right.
And like exploding basically from the outside in. And at that point, it's very dramatic. It's very sudden.
That's gonna look amazing.
Yeah.
Do you think, like, obviously you don't want to be around for that, but do you think there's any chance whatsoever that humans are going to be around for the finale for as long as life can be around for the finale? Do you think like our future, we have a chance at all?
I don't know. I mean, the first thing we have to figure out how to do is survive the death of our sun, right? And that's non-trivial, right? That's a big deal. We only have about 1 billion years before Earth is no longer habitable.
Yeah.
Because in 1 billion years, the sun will puff up enough to boil off the oceans of the Earth. And then, a few more billion years after that, the sun becomes a white dwarf and is basically useless.
Yeah.
So we have to figure out how to get through that hump, right?
Yeah.
And I kind of feel like if we're able to do that, if we're able to find a way to leave Earth and, be sort of free-floating out in the universe and making use of whatever energy sources we find, I think that gives us a significantly better chance of making it into some indefinite future. I don't know.
Yeah, because then we can start hedging our bets and going to all sorts of places.
Yeah, exactly. But
1 billion years seems like enough time to figure it out.
you would think so, but I don't know. I mean, we've had what 50 years on climate change and we've done nothing. So I'm not sure how much I'm not sure how much faith I have in humanity on that scale.
Oh, don't start me on your climate change, Katie Mack. Go and learn some science.
Yeah, sorry. I'll get right on that.
I set it up for you. So, I mean, obviously the sun won't be around for the end. Mm-hmm. Does the Milky Way make it to the end, or does the Milky Way turn off before the end as well? Like, do we run out of gas and stars here?
Well, so it depends on when you think it's happening. I mean, so there's the heat death is the sort of ultimate end of the universe that we think we're probably heading to, where, it's sort of defined by all structures over by then anyway. So it's nothing can survive to the end of that because, it's not the end if anything's left.
Yeah.
Other scenarios that could, in principle, be sooner. I mean, if we were going to have a big crunch, like we probably can't because we're pretty sure the universe is going to keep expanding forever. But if it were to stop and turn around, we're pretty sure that couldn't happen for, tens of billions of years at least. But if it were tens of billions of years and not longer, then in principle we could be around for that. But, again, we don't really have a good reason to believe that could happen or a mechanism for it happening. So that's pretty unlikely.
Yeah.
The Big Rip, if the Big Rip were going to happen, then the earliest that could happen and be consistent with current data is about 200 billion years. And in principle, there will be some stars in the Milky Way still around in 200 billion years. So, the universe won't be totally dark and empty by then. And something could in principle be around to see that happen. And then there's vacuum decay. I mean, vacuum decay could happen in principle at any moment. It's just that if it did, you wouldn't see it coming.
Right.
And it would happen so fast that you wouldn't necessarily really notice it. So that one probably won't happen until long, long after everything is kind of fallen apart. But you can't say with certainty that it won't happen sooner.
I don't know much about this vacuum decay because the next question, one of the final questions I wanted to ask you is there like a universe equivalent of, the asteroid that came out of nowhere and just whacked you in the face, the thing that scientists can't predict?
Yeah, totally.
Is that what vacuum decay is?
That's absolutely what vacuum decay is. Yeah. So vacuum decay, it's this sort of newish idea in the sense that it's gained more popularity recently. The idea behind vacuum decay is, our universe has a Higgs field. So it's this sort of energy field that pervades all of space. And the Higgs field is sort of connected with how physics works, like what it sort of determines the laws of physics, the interactions between particles, just how physics works on a fundamental level. And we know that the Higgs field was different in the very early universe. So when you hear about the Higgs boson is this particle that's associated with this energy field. And discovering the Higgs boson was a big deal because it indicated that our ideas about the Higgs field was correct, that the Higgs field is this energy field that's throughout all of space, that it did undergo a shift in the very early universe that sort of set up the conditions for particle physics as they are now. And so finding the Higgs boson was an indication that, yes, we do live in a universe like that where this Higgs field made a change, and that change determined how physics works in our universe.
Yeah.
The problem is that measurements of the Higgs boson, our increasingly better understanding of the Higgs field, suggests that the value the Higgs field has now is not necessarily the sort of preferred value. It suggests that the Higgs field could change again.
Right.
And we don't want the Higgs field to change again, because if it did, we would have totally different laws of physics. Our particles wouldn't hold together anymore. We couldn't have atoms and molecules.
Right.
It would destroy all structure in the universe, right? So we don't.
Oh, that sounds bad.
Yeah, we don't want that to happen.
That would definitely affect my Wi-Fi.
Yeah. No, it's a problem. And the issue is that we think that the Higgs field might be metastable in the sense that if it were disturbed a little bit, it could sort of revert to this other value and change the laws of physics, or alternatively, it could undergo a quantum tunneling event at one point in space where the Higgs field could quantum tunnel to this other value. So it would just sort of spontaneously change in one point in space. And at that point in space, it would create this bubble of what we call a true vacuum, a different kind of space in which the laws of physics are different inside that bubble. And that bubble would then expand out at about the speed of light and destroy everything in its path. And then the space inside the bubble, this true vacuum space, in principle is most likely gravitationally unstable. And so once the bubble wall hits you, first the bubble wall incinerates you because it's got a lot of energy in it. And then you're inside the bubble and your molecules don't hold together anymore. Particle physics is totally different. And then the space inside gravitationally collapses, so you sort of turn into a black hole.
Okay. Is there anything we can do to prevent this from happening, to stop this event from occurring?
No, not at all. There's nothing we can do.
Right.
And because it's based on quantum tunneling, it's a probabilistic event. It's based on quantum physics. So you can't even predict when it's going to happen, where it's going to happen. All we can do is, based on our calculations of our current understanding of particle physics, we can put probabilities on when it might occur. And we can say that, it sort of has a half-life, right? We can say that it's probably not going to happen within the next, 10 to the power of 100 years. That's sort of our best estimate at the moment. But we don't know for sure.
If it happens, does it happen at a specific location?
Yeah.
So it could have already happened so far away and be coming towards us without us knowing?
Yeah, I mean, if it happened, next to Saturn right now, we wouldn't know for another hour or so, right? Like, it's
okay.
It could just be the bubble could be coming toward us at the moment, and we wouldn't be able to see it until it was on top of us. So,
wow.
So yeah, I mean, it's very unlikely for it to happen anytime soon, but we can't entirely rule that out.
But you're saying there's a chance.
Yeah. Yep.
Well, on that note, I feel like I better get to work editing this podcast because
you never know.
I don't know if people are going to hear it otherwise.
Yep.
Well, that's all for now. You can learn more about Katie's work, her tweeting, and perhaps most importantly, her doomsday book in the notes for this episode. Thanks again to G Research for supporting this podcast. They're also in the notes. And yes, thanks to MSRI, the Mathematical Sciences Research Institute, for supporting Numberphile. I'm Brady Harron, and you've been listening to the Numberphile podcast.